All right, hello students. This week we're going to be covering NMR spectroscopy. You'll notice the format's a little different this week. We're doing a entirely online format because this is a dry lab. Okay, we don't have an NMR instrument. This is an NMR instrument here, but nevertheless, NMR spectroscopy is an important technique for you to understand, especially for deciphering your unknown compounds. So, what is the purpose of NMR spectroscopy? The purpose is to decipher the structure of a molecule, so the arrangement of the bonds and the atoms in a molecule. Okay. There are four main principles that you need to understand in order to basically problem solve any NMR problem. The first principle is that a signal, so a signal is the peak you might see in a spectra, is produced by a unique type of hydrogen. So depending on how many types of hydrogen you have, that will influence how many signals you have, and it's a 1-to-1 ratio. So we'll go into more detail about each of these in the following slides. The next principle is integration. So each of these signals has an integration value. So if you remember from calculus, integration is the area under the curve, and that curve corresponds to the amount of hydrogen that produced that signal. So how many hydrogen produced that signal. The third principle, chemical shift. So this is where it is on the left-right plane, on the x-axis. So the position of that signal, left or right, will tell you what groups of the hydrogen that produced the signal, remember, produced the signal, are next to. So whether that be next to an electronegative atom or next to a non-electronegative atom. Okay, and the final thing is splitting. So splitting is what the signal looks like. So is it split into how many lines, a singlet, a doublet, triplet, etc. And that tells you, this is perhaps the hardest part to understand, this tells you how many hydrogen neighbors there are. Okay, so not how many hydrogen produce the signal, but how many hydrogen are adjacent or right next to the hydrogen that produced the signal. So neighbors. Okay, so let's look at an example. So here we have an NMR spectra. This structure right here is ethyl acetate. That's the structure we're looking at. And I like it because it has some very easy to decipher structural features that you see a lot throughout many organic compounds. So the first aspect, the number of signals equals the number of hydrogen types. So in this molecule, you can see we have 3 types of hydrogen, okay? And here they are. So we have one type here. These 3 on the CH3 group here contribute are one type of hydrogen, okay? So these 3 are equidistant to this carbonyl. They're all equivalent. The next type is this CH2 group. So these 2 hydrogens are in the same chemical environment. They are next to this oxygen. This is the second type, and this is the third type right here. So these 3 hydrogen are a CH3, but they're different from this CH3 because they're next to a CH2. Okay, so I know it sounds a little redundant to go to explain how these 2 groups are different, but nevertheless they are. So we have 3 types of hydrogen, and therefore we have 3 signals. So if you see one signal here, okay, we have one signal here, and then we have one signal here. Okay, so 3 types of hydrogen, 3 signals. And this will hold true for all types of organic compounds. So if you had a compound with 5 signals, that would tell you there are 5 types of hydrogen. Okay, so 3 signals, 3 types. Integration. So integration tells you how many hydrogen contribute to each signal. So for example, this 2 right here, okay, represents that there are 2 hydrogen that are producing this signal. Okay, this 3 right here tells you that there are 3 hydrogen that produce this signal. And then these 3 hydrogen produce this signal, this triplet here. Okay, and already you can see we can start to assign these peaks to these to this structure. So we might say that this 2 can only belong to this type of hydrogen. Okay, because this is the only signal with an integration of 2. What we don't really know at this point is which peak these 2 types of hydrogens belong to. So this one here and this one here, because they both have 3 hydrogen, and as you can see, the integration of these 2 peaks are also 3. Okay, so we're just piecing together the puzzle here. The last principle here is chemical shift, and this is what will allow us to decipher which peak belongs to which. Chemical shift is the XY or the x-axis here. So it usually runs from anywhere from 12 on the left. The spectra here is zoomed in, but 12 on the left to 0 on the right. Okay, so for example, if we identify this quartet here is at about 4.2. Okay, this singlet here is at about 2.1, and then this triplet here is at about 0.8. Okay, and these tell you what groups they're next to. If a group is farther to the left is sometimes referred to as downfield. This tells you that it's close to an electronegative atom, such as oxygen. So this integration of 2, giving a quartet, is probably this CH2 right here. These two hydrogens are producing this signal. Conversely, if a signal is to the right, farther to the right, or upfield, it's farther from an electronegative atom. So this CH3 here, okay, 3 hydrogens, are probably these two because they're farther away from the oxygen. Okay? And that sort of gives you an idea of how to decipher an NMR structure or a spectra based on these features. Okay? Splitting, let's talk about splitting. So in splitting, we're talking about how many neighbors a particular signal has. So if we identify, this is our quartet here, so you can see it has 4 little blades of grass, you might say, or 4 peaks. That's a quartet. Okay? That's a singlet here, so it has just 1 peak. And then that's a triplet. So 1, 2, 3 peaks. Okay? And these peaks are given by the n+1 rule. And the n+1 rule says that the number of neighbors, hydrogen neighbors, plus 1 gives you the splitting value. And then splitting values are fairly intuitive. So if you have a split value of 1, you get a singlet. So for example, this is 1, the quartet is 4, and then the triplet is 3. And for the n+1 rule, it's pretty simple. So if you have 1 neighbor, you get a doublet. If you had 2 neighbors, you get a triplet. 3 neighbors, you get a quartet, and so on and so forth. Okay? So if we look at this right here, these, oops, let's go back. If we look at this CH3 right here, these 3 hydrogens have 0 neighbors, 0 hydrogen neighbors. And a neighbor is a hydrogen within 3 bond lengths distance. So if you go 1 bond length, 2 bond length, 3 bond length. Okay, well there's no bonds on this carbon right here that are connected to any other hydrogen. Therefore these hydrogens have no neighbors. And if you have no neighbors, you get a singlet. So it's probably fair to say that these hydrogens give you that signal. Okay, singlet. If we look at these hydrogens, okay, so these hydrogens here have 3 neighbors. So if you go 1, 2, 3, okay, these 3 hydrogens are within 3 bond lengths distance, therefore they are neighbors. So 1, 2, 3 neighbors plus 1 gives you 4. And a splitting of 4 is a quartet. So these hydrogens probably give you this quartet. And then lastly, by process of elimination, these 3 give you the triplet. And that occurs because these have 2 neighbors. Okay, so these hydrogens have 2 neighbors. 2 plus 1 is 3, and 3 is a triplet. So these hydrogen give you that signal. Okay, and you can see how useful it is to decipher a structure using these techniques. Let's go over a common splitting pattern. If you see a quartet that integrates to 2 hydrogen, and if you have a triplet that integrates to 3 hydrogen, that's probably an ethyl group. So the ratio here is a 2:3 ratio of quartet to triplet. And it's very common that these are ethyl groups, CH2, CH3. Okay, just to keep that in mind. The other common trope is the alpha to carbonyl hydrogen. So these hydrogen here are alpha to this carbonyl. They're on the alpha carbon. And these hydrogens like to show up at 2.1 ppm. Okay, around 2.1 ppm. So whenever you see a signal, it might not be a singlet, though often it is. But if you see a signal near 2.1 ppm, there's a good chance that these hydrogens are 1 away from a carbonyl. Okay, so these types of hydrogens. The last thing I wanted to cover is the degree of unsaturation. This is sometimes called the hydrogen deficiency index, or HDI, or sometimes just called index. And this helps you look at a molecular formula and deduce whether that molecular formula has any double bonds or rings. So this is a nice infographic from Mastering Organic Chemistry. I like it very much because it has a very simple formula here. And it allows you to calculate this degree of unsaturation using simple arithmetic. So if we have this structure, ethyl acetate, which we just looked at, this is the molecular formula, C4H8O2. What we can do is we can take this molecular formula and input it into this equation. So here's the equation here, 2C plus 2 plus the number of nitrogen minus the number of hydrogen minus the number of halogens divided by 2. In a simple molecule like this without any nitrogen or halogens, these two values here are 0. Okay, so if you plug and chug, the 4 gives you this 4 carbons here. There are 0 nitrogen, there are 8 hydrogen, and there are 0 halogens. So if you perform this expression, divide by 2, you get an index of 1. And what that means is, an index of 1 means that there could be one double bond or one ring. Okay, so in this case, it's not a ring, it's one double bond. And that double bond counts as the carbonyl here. So it may not be an alkene, it might be a double bond. Okay, let's look at a more complicated example. Here we have cyclohexanone, which has the formula C6H10O. And if we perform the same expression, we get an index of 2. So if you get an index of 2, that means the total number of multiple bonds and rings equals 2. So you can examine this infographic in more detail in your spare time. But the conclusion we draw from this is that this structure has 2 double bonds or 2 rings or 1 double bond and a ring. Okay, so no matter what you do, you're going to have 2 degrees of unsaturation, hence the name. Okay, so if you didn't know this structure here, this molecular formula and this equation could help you decipher whether it has any double bonds, rings, or both. Okay, it might be one of these. And the NMR will help you decipher whether there are 2 rings, 2 double bonds, or a bond and a ring. Okay, so thanks for watching. We're going to move on to another website which will help you perform exercises to help you with NMR problems. All right, hello students. Now we're going to go to this website here, cheminfo.org, to basically do some NMR exercises. So we'll put this link in the Canvas, on the pages in Canvas, for you to go to and practice on your own. But basically this website lets you practice various NMR problems, and I encourage you to explore them so that you develop a better sense of how to solve NMR problems. Let's do the first exercise, which is number of signals. Okay, so here we have a list of exercises. You can see there's no structure here, and here's some instructions so you can read these on your own time. The only thing I would say is maybe disregard these terms here. So these terms, homotopic and antiotopic, diastereotopic, they're not very germane for our purposes. They're not really relevant, so you can disregard those. So if you read the instructions, the first thing to do to this exercise is to click on here. Now, the purpose of this exercise is to deduce or to predict how many signals you would see in an NMR spectra. And if you remember from the PowerPoint, if you have one signal, that corresponds to one type of hydrogen. So how many types of hydrogen will tell you how many signals there are in the spectra. So if you have this molecule here, ethane, okay, you can see it's a fairly symmetrical structure, so it's probably going to have a lot of equivalent hydrogens. And if you highlight them, you can actually see that these hydrogens are all equivalent. So this CH3 group here is indistinguishable from this CH3 group. Okay, so all of these hydrogen would produce the same signal. So my answer I would expect is 1. So you type your result in here, and if the answer is correct, it'll be green. Okay, so green. This structure here will produce 1 signal. Let's look at another one. So here we have propane. Okay, and propane, it's a little bit bigger, but it's still fairly symmetrical. So you can see maybe that these 6 here, these 6 hydrogen in yellow, are equivalent. So this CH3 on the left is identical to this CH3 on the right. These hydrogens are identical to these. And that's because they're both equidistant to this CH2 group here. Okay, so they're indistinguishable. So these would make 1 signal, and then these 2 hydrogen would produce the other signal because they are different. So these are CH3, but these are CH2 hydrogens. Okay, so this molecule in total would produce 2 signals. Okay, here's another molecule. We have pentane. And pentane is going to have 3. So these 6 hydrogen here, so the CH3 on the left and then the CH3 on the right, produce 1 signal. These 2 CH2 groups are equivalent, right, because they're both kind of symmetrical, equidistant from this CH2 group, and they're equidistant from their terminal methyl groups here. So these 4 hydrogen would give you another signal. Okay, so 1 signal, 2 signal, and then this CH2 in the middle would give you your third signal. So in total you would expect 3 signals. So put 3, it's correct. Okay, let's exercise 4. Okay, here in cyclohexane, it turns out that all 12 of these hydrogen are actually equivalent. Okay, they are indistinguishable from one another, and that's probably because the molecule is perfectly symmetrical no matter how you slice it. So there's no way to distinguish one of these hydrogen from the other. So you would expect to see one signal. Okay. Here we have toluene. So this is a more interesting example. So here, this CH3 is obviously one signal. Okay. Now these two hydrogen are equivalent. So these two in yellow, this one and this one. And that's because they are equidistant to this methyl group. So it's as if there's a line of symmetry going down this molecule here. In fact, maybe we can draw it here. Okay, so you have a line of symmetry. Let's use a darker color here. So if we draw a line down this benzene ring, you can see that there's a line of symmetry here. So these two hydrogen are equivalent. Okay, so these two. Now these two are also equivalent. Okay, they are equidistant from this methyl group. Okay, so this is another type. And then this hydrogen here is the last type of hydrogen. So it's unique from the others. So 1, 2, 3, 4. So you would expect to see 4 signals. Okay, how about this one? So here we have dimethylbenzene. This is the ortho dimethylbenzene. So because there's once again a line of symmetry going from top to bottom, these three methyls, or these two methyls, and their 6 hydrogen produce one signal. Okay, this one hydrogen is unique. Okay, these two are unique, and then this one is unique. So you'll notice that these two hydrogen on the top here and the bottom are non-equivalent, and that's because one of them is closer to the methyls than the other. So this one at the bottom is closer to the methyl groups than this one. So in total, you expect 1, 2, 3, 4 signals. Okay, how about one more? So here is another interesting case. Now this is another perfect molecule, very symmetrical. So there's a line of symmetry here and there's a line of symmetry here. So in fact, these two methyls are equivalent because of the line of symmetry here. Okay, and these 4 are also equivalent. Okay, so there's no way to distinguish these two on the left, so this one and this one, from these two on the right. So this only has 2 types of hydrogen. These hydrogen here and these hydrogen on the methyl. So you would expect to see 2 signals. Okay, so I encourage you to work through that. Hopefully that gave you a sense of how these problems are and how many signals you would expect in the spectra based off the structure. And I encourage you to work through this up to about, let's see, 15. Don't go farther than that. 16 through 21 get fairly challenging, so you can do those on your own time. We're going to work on some NMR problems that are more similar to those that you're going to be doing in the worksheet. So here on the website, we're going to go to this exercise right here, structure from proton NMR. Okay, now that the website's loaded, you can see that there are various exercises here, 1 through 7, and there's actually more if you go back to the previous screen. But the goal of these exercises is to take this molecular formula, and if you click on it, it will generate the spectra, and you're going to try to figure out what the structure of these molecules are based on this spectra. And you will basically draw the organic compound in this box here, and that will help you decipher the structure, the spectra. Okay, so what we're going to do is the first thing is to calculate the index for this molecule. So the index of this molecule, if you calculate it, so let me move this down here, the index of this molecule is actually equal to 1. Okay, 1. So that tells us that there is either one double bond or one ring with this structure right here, C3H6O2. Whenever you see 2 oxygens in these types of compounds with an index of 1, it's usually a pretty good indication that there might be an ester functional group. So if I can draw an ester here, R, and then O, R. So these 2 oxygens are what are these 2 oxygens in the molecular formula. Okay, so another thing to note in the spectra is that there are only 2 signals. Okay, so there are only 2 types of hydrogen here. So based on this information, we can already suggest a structure that may be the answer. So if I draw out an ester here, O, and then imagine this is R, and then here is O, and then R. If we simply fill in the blanks and say, well, we've used 1 carbon and 2 oxygens, if we just replace these R groups with carbon, we actually arrive at the correct answer. So the answer is methyl acetate here. Now, because it's a small molecule, it only has 3 carbons, and we arrived at the answer very easily. It's still good to check, to verify that this structure matches with this spectra. So I'm going to add hydrogen here, just so we can see them. Okay. So in this case here, we want to make sure that each signal in the spectra we can assign to a certain type of hydrogen in our molecule. So this singlet at about 3.5 ppm right here probably corresponds to hydrogen that are next to an electronegative atom. So these types of hydrogen here on the methyl connected to the oxygen, or these types of hydrogen connected to the carbonyl. So these are connected to a more electronegative atom here, these hydrogens, so they probably correspond to the signal here. Okay, and this these 3 hydrogen, remember the integration is 3, these 3 hydrogen at about 2.1, remember 2.1 is kind of like a magic number, tells us that those hydrogen are probably adjacent to a carbonyl. So it would be these 3 right here. Okay, and it makes sense too that they're singlets. So singlets, remember, via the n+1 rule, if it's a singlet, that means n equals 0. There are 0 neighbors that these hydrogen have. So these 3 hydrogen have 0 neighbors, and these 3 hydrogen have 0 neighbors. Okay, let's try the next problem. Okay, so here we have C3, excuse me, here we go, C3H6O. You can see the formula is very similar to the previous question. We're just missing 1 other oxygen. That also means that the index is the same. So if you calculate the index is exactly the same. It's probably going to be a double bond and not a ring. So instead of it being an ester this time, since we don't have another oxygen, it's probably going to be a ketone. Oops, draw a ketone here out. Then 2 R groups, carbon fragments, just like that. So if we do that and we simply draw a ketone here, we may arrive at a similar state where we can kind of predict the structure, since it's so small, just by drawing the skeleton of what we think it might be. So acetone turns out to be the correct structure here. So we've used up all the atoms in our molecular formula, so this entire structure is C3H6O. And if we add in the hydrogen, we can do the same exercise and make sure that each type of hydrogen we can correlate to the peak on the spectra. Now in the spectra there's only one signal right here, a singlet at about 2.1 that integrates to 6 hydrogen. So in this case, all 6 of those hydrogen, let's see if I get my pen here, all 6 of these hydrogen here are equivalent, okay? And that's because the molecule is symmetrical down the center. So these 3 and these 3 are all symmetrical, and they all contribute to the same signal, which is a singlet at 2.1 ppm that integrates to 6. So another fairly simple example. Okay. This next problem is very similar as well. You can see that the molecular formula is exactly the same as exercise 2. So the index is still 1, but now instead of having 1 signal, we have 3. Okay. So if we zoom in a little bit here, we can sort of decipher what these signals are. If we look at this one, this is a triplet. So the one at around 9.6 is a triplet. Keep that in your mind. The one here at about 2.5, this is a 1, 2, 3, 4, 5, 5. It is a quintet or a pentet, so 5, that's the splitting. And then here at about 1 ppm, this is a triplet. Okay, so those are our 3 signals. So we should label them to make sure we know what they are. So this one here is a triplet. Okay, this one here is a pentet or quintet, like pentet for 5, pentagon. And then this one here is a triplet. Okay, so triplet. So remember, it has the same molecular formula as the previous question, so it's going to be very similar. The most unique aspect of this spectra is the peak here above 9 ppm, in between 9 and 10. And these sorts of interesting chemical shift values, it's good to have a table. There are many tables that show chemical shift values. So if we go to your textbook, so this right here is the Smith textbook, you can see there's a list of ppm values here for the various types of hydrogen on your molecule. And conveniently here at the beginning is the aldehyde, which is what we're after. Aldehydes, this hydrogen connected to the carbonyl shows up at around 9 to 10 ppm. So that's a good indicator that in our spectra, this molecule here, or this peak here, probably corresponds to a aldehyde. So what we can do now is, in our structure, we can draw in an aldehyde. Okay, so there's our aldehyde, and then R would be right here. Since we've used one carbon, we might as well just add 2 more. And what do you know? The answer is correct. So let's draw in our hydrogen. Specify that those lines are hydrogen. Okay, and now we can see that this structure here corresponds with this spectrum fairly well. So let's pull up our drawing tool. Okay, so this hydrogen right here is, as we said, our aldehyde hydrogen. So this hydrogen is around 9.5, which is right in the range. It integrates to 1 because there's 1 proton, but the splitting is also interesting. It's a triplet. So a triplet means that it has 2 neighbors, and the 2 neighbors are right here, this neighbor and this neighbor. So these 2 hydrogens will split the aldehyde hydrogen into a triplet. Okay, this triplet right here, I think is more simpler than the pentet. So this triplet comes from these 3 here, these 3 hydrogen at the methyl end. So if it's a triplet, remember it has 2 neighbors, so the 2 neighbors are once again these 2, and it integrates to 3. The pentet is perhaps the most interesting here. These 2 hydrogens give you the pentet, and that's because it has 4 neighbors. So the aldehyde hydrogen plus 3 methyl gives you 4. 4 plus 1 is 5. 5 is a pentet. So, and as you can see, the closer these groups are to the carbonyl, the more downfield they are. So if you compare the pentet, hydrogen here to the triplet hydrogen here, you'll see that the pentet hydrogen are further to the left because they're closer to the carbonyl. Once again, around 2.1, 2.2 ppm. Okay, so now we can go on to the next problem. Okay, in this problem we have C6H12. If we calculate the index is 1. So that tells us there's going to be either a double bond or a ring. Now, because there's no oxygen in this structure, it's not possible for there to be a carbonyl as the double bond. So in this case, we might be thinking that, oh, this is probably a ring of some sort. A ring. And because there's only one signal, it's probably a simple ring that's very symmetrical. In fact, C6H12 corresponds nicely to the structure of cyclohexane. So if we draw cyclohexane here, we get the right answer. So why is cyclohexane the correct answer? Well, the one signal here is generated by all 12 of the hydrogens. So let me just draw in one of the CH2s. So there are 6 CH2s around this ring here. These 2 hydrogen here are just one part of the entire signal. So imagine all 12 of these hydrogen giving you this signal right here. So since they're all equivalent, they all generate the same signal here. So that was a fairly simple question. Okay, this question is a bit more complicated. We have C9H12. So the index here is special. It's very high. So the index for this molecule is 4. 4. Now, the other thing to note is that we have some signals in the aromatic region. So if we go to our table here of values, if we go to the aromatic compounds, the hydrogen connected to these rings tends to show up between 6.5 and 8, depending on what kind of groups you may have, electron withdrawing or electron donating groups, but within this region. And in our spectra, we do have some signals there. And conveniently, benzene rings have an index of 4. So a benzene ring consists of 3 double bonds and 1 ring. So 3 plus 1 giving you an index of 4. So chances are, for this problem, we're dealing with some sort of aromatic ring. So let's just draw in benzene to start. And then that has already used up 6 of our carbons. Okay. Then we have this oxygen to contend with. So because we've used up all 4 of our index values, so making this benzene ring, our oxygen is probably going to be in alcohol, OH, or in ether, OR. Now, it's probably not an alcohol because the OH will show up as a broad singlet somewhere on this spectra. But if we zoom in here, we can see that all of these are nice multiplets. So there are triplets, doublets, etc. None of them are singlets, and they're not very broad. They're very sharp. So it's probably going to be an ether of some sort. And the ether is probably going to be connected somewhere to the benzene ring. So if we go here, connect to alcohol, and conveniently we can just fill in the other carbons. So we have 6 carbons here. We have to use 3 more. So if we just add 1, 2, 3, we end up getting the right answer. Okay, so sometimes when you approach an NMR problem, sometimes you kind of generate a structure and then check to make sure that it's consistent with the spectra you're given. So in this case, let's draw in the hydrogen and examine why this is the correct structure. So H. Okay, so here in our spectra, we have 1, 2, 3, 4, 5, 6. We have 6 types of hydrogen, and in our molecule, you can see that we do in fact have 6 types. We have these 3, we have these 2, we have these 2, so these are 3 types. These 2 right here that are ortho to the oxygen are the 4th type. These 2, which are meta to the oxygen, are the 5th type, and then the 6th type is the hydrogen that is para to the oxygen. Okay, and we can assign these peaks to these hydrogen to the signals in the spectra. So if we start with, let's just start with the aromatic region, because I think that's going to be the most complex. So let me exit out of here real quick, and we'll zoom in so we can see the aromatic region. So we're just focusing on the 3 types of hydrogen in the aromatic region. Okay, so these 3. As you can see, they integrate to 5, and we have 5 protons here, so it makes sense. Let's pull up the drawing tool. This triplet right here, it probably corresponds to these 2 hydrogen right here. So this hydrogen and this hydrogen probably give you this triplet. So it integrates to 2. There are 2 hydrogen, they're equivalent, and they have 2 neighbors. So if we examine this hydrogen right here, you can see that they have 2 neighbors, 1 and 2. So 2 plus 1 gives you a triplet. Okay. These 2 hydrogen, okay, these probably, you can see that this spectra has been integrated such that these 2 peaks are actually equal 3. So this one right here is actually has an integration of 2. And then this one, it has the remainder integration of 1. Okay, so these 2 hydrogen correspond to these 2 hydrogen right here. And that's because these each have 1 neighbor. So if you examine like one of these protons, this hydrogen is its neighbor. So 1 plus 1 is 2, giving you a doublet. Okay. Finally, this proton here gives you the triplet. So instead of having an integration of 2, it's an integration of 1, and it has 2 neighbors. So this neighbor here and this neighbor here. So 2 plus 1 is a triplet. So this is the aromatic region of this portion of the molecule. Okay, let's examine the final 3 signals. So now we're going to focus on these 3 carbons here. Let's pull up the tool. So let's talk about the chemical shift values. So if we look at the chemical shift values, you can kind of see that as they come closer to the oxygen, they're probably going to be more downfield. So these 2 protons here probably correspond to that signal right there. So these 2 protons have 2 neighbors. So their 2 neighbors plus 1 gives you a triplet, so it's a triplet, and it integrates to 2. So that makes sense. As you move farther away from the oxygen, your chemical shift value will go closer to 0. And in fact, these 2 protons give you the pentet there. 1, 2, 3, 4, 5, 6. I'm sorry, hextet. 1, 2, 3, 4, 5, 6. Yep. So they have 1, 2, 3, 4, 5 neighbors, and 5 plus 1 is 6. So this is your hexat that integrates to 2, because there are 2 hydrogen here. Okay, and then finally, the farthest away from the oxygen is the most upfield, closer to 0, and that gives you the triplet that integrates to 3. So 3 hydrogen, 3, and they have 2 neighbors, so it gives you a triplet. Okay, for this structure, we have C3H7Cl. And for this structure, the index equals 0. So an index of 0 means there are no double bonds and no rings. You can also see that there are only 2 signals there. So there's only 2 types of hydrogen here, indicating that the molecule is probably very symmetrical. Okay, so if we simply draw a 3-carbon backbone, and then we can also assume that one of those carbons is going to be bearing the chlorine. And if we think symmetrically, if we put the chlorine in the center, we get the answer. So here are the 2 types of hydrogen. So I'm going to add in the hydrogen. There. And we have the answer. So let's make sure that this structure makes sense. So let's zoom in here on our signals. Okay, this signal right here, it's very difficult to see, the one at 4. So if we kind of exaggerate the spectra here, you can kind of see that there are these little peaks here that you may be difficult to see, but it's actually 1, 2, 3, 4, 5, 6, 7. So it's a septet, 7. That's the splitting pattern here, 7. Okay, and then this one right here is a doublet. Okay, so keep that in mind. The one on the left is a septet, 7, and the one on the right is a doublet, 2. So when we assign our spectra, or assign the protons to the signals, it'll make sense. So let's start with the simple ones, these 3 here. If you didn't want to analyze the splitting pattern first, you can kind of just decipher the structure from the integration. So an integration of 1 means there's 1 hydrogen, so it's probably this hydrogen right here. And conversely, these have an integration of 6, so it's probably going to be these 6 here. So these 6 on the adjacent carbons. Okay, so this hydrogen gives you the septet because it has 6 neighbors. So 1, 2, 3, 4, 5, 6. So 6 plus 1 is 7, septet. You can also note that it's above 4 ppm, and that's because it's alpha to this chlorine group. Chlorine is a very electronegative atom, which de-shields this proton, making it very downfield. These 6 methyl hydrogen are much more upfield because they're farther away from the chlorine, and they have a splitting pattern of a doublet, and that's because they only have 1 neighbor in the center. So 1 plus 1 is 2, which is a doublet. Okay, finally we have this structure, C6H15N. Okay, if we calculate the index for this molecule, we find that it has an index of, just like the last problem, 0. Okay, so in this case, no rings and no double bonds. Okay, let's zoom in and figure out the splitting pattern on these, on this molecule. So there are only 2 signals, and those 2 signals are a quartet and a triplet. And in fact, they have an integration ratio of 6 to 9, which is 2 to 3. And whenever you have a quartet triplet in a 2 to 3 ratio, it's a very good chance that it's probably an ethyl group. Now, if you think about it, an ethyl group is 2 carbons, but we have 6. So the likelihood is that we don't have 1 ethyl group, we actually have 3. And if we simply draw in a nitrogen, so here's a nitrogen, and we add 3 ethyl groups, okay, we arrive at the correct answer. So in this case, I'm only going to draw on the hydrogen on one of the ethyl groups just to see it. H, 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 H. And then we can assign each of these types of hydrogen to their peaks. Okay, so these hydrogen here that are next to the nitrogen give you the quartet here. Okay, and that's because they have 3 neighbors. Remember, there are hydrogen here as well that are equivalent to these 2. So the ethyl groups are equivalent. Okay, and they integrate to 6, so 2, 4, 6. And they have a quartet because they have 3 neighbors. 3 plus 1 gives you a triplet. Also note that they're more downfield because they're adjacent to the nitrogen, whereas the methyl group here, this methyl group at the end, okay, gives you the triplet. Okay, and that's because they have 2 neighbors. And they're closer to 0, they're more upfield because they are farther away from the nitrogen. Okay, and then keep in mind there's There are also a CH3 here and a CH3 here, and the hydrogen on these two are equivalent to these. So they integrate to the 9 integration on this triplet here. Okay, and that is the end of the exercises in this module. But I would like to point out to you that on this website they have more exercises that I encourage you to try. The only way to really understand how to solve NMR problems is to do it yourself. So if you click on this one, this is the other set of exercises, and you can try these out on your own. As we stated before, we'll put this link on Canvas, and we'll see you next week.